Dear students, today we will discuss phase rule. Now, what is phase rule? Based on thermodynamic considerations, J. Willard Gibbs put forward the phase rule for studying the heterogeneous equilibrium. The phase rule is a relation between the number of components, the number of phases, and the variable parameters of a heterogeneous system in equilibrium. That is, F equals to C minus P plus 2. Before proceeding with the deduction of the rule, it is necessary to define the terms involved, namely phase, component, and degrees of freedom. So, we will first discuss the phase, component, and degrees of freedom. Now, what is phase? A phase is defined as any homogeneous and physically distinct part of a system which is separated from other part of the system by definite boundary surface. Now we can understand phase with some examples. First example, a system containing water and its vapor in a closed vessel has two phases, the liquid phase and the vapor phase. Here it is the case. Now, it is liquid, pure liquid, and above the pure liquid there is vapor. Now, this is the surface of separation, that is the separation, boundary of separation between liquid and vapor. So, distinctly there are two phases. One is the vapor phase and the liquid phase. Next, a gas mixture. A gas mixture is always a single phase. Since gases are completely miscible with one another in all proportions. Since gases are completely miscible with one another in all proportions. Here is a gas. Here is a gas enclosed in a cylinder. The gas may be a single gas or a mixture of gases. Now, this is a single phase. It may be a single gas or a mixture of gases. So, a single gas or a mixture of gases, whatever it may be, this is a single phase system. Now, for liquids, the number of phases is equal to the number of layers present in the system. For completely miscible liquids, the number of phases is equal to 1. If we take a pure liquid or a homogeneous solution, whatever it may be, this constitutes a single phase. There is no any surface of separation inside the liquid. So this is a single phase system. But if we take two immiscible liquids, there is two immiscible liquid pair. There is an immiscible liquid pair. It is the immiscible liquid pair. There is liquid A and liquid B. Here is a distinct boundary of separation between these two. This is the boundary of separation between these two. So this is a two-phase system. This is phase 1 and this is phase 2. Now, solid systems. Every solid constitutes a separate phase except when a solid solution is formed. We will discuss the solid solution later. But if we take two solids in contact with each other, then definitely there are two phases. Let me consider the solid A and solid B. They may be even in their molecular state. There is a distinct surface of separation between these two. This is the distinct surface of separation between A and B. So A is one phase and B is another phase. So this is a two-phase system. So solids, if we take different solids, then the number of solids will be the number of phases. All homogeneous solutions are one-phase system, which I have already discussed, whatever may be the number of substances within the system. Now we will discuss components. What is component? It is the minimum number of independent chemical constituents by which the composition of each and every phase of a system can be expressed. I repeat, it is the minimum number of independent chemical constituents by which the composition of each and every phase of a system can be expressed. Hence, the independent chemical constituents refer to that one whose concentration can be varied independent of other constituents of the system. So, we can understand this from some examples. Let me take some examples first. It is to be noted here that components of a system are not synonymous with the constituents of the system. If there are three constituents in a system, it is necessarily not that the component of the system will be three. So components of a system are not synonymous with the constituents of the system. The first example one. Let we take the system liquid water is in equilibrium with water vapor. It is an one component system. Why? Both the phases, the liquid phase and vapor phase, may be expressed by one chemical entity, that is H2O. That is, this water phase can be expressed as H2O, the vapor phase can also be expressed as H2O. So this is a single component system. Same is the case for solid water in equilibrium with water vapor. Here solid water is expressed as H2O and water vapor is also expressed as H2O. Solid water in equilibrium with liquid water, solid water is expressed as H2O, liquid water is also expressed as a single entity H2O. So this is a single component system. When three states, that is solid water, liquid water and water vapor, are in equilibrium, it is also a single component system because solid water is expressed as H2O, liquid water also expressed as H2O, and water vapor is also expressed as H2O. Now there are some general principles to ascertain the number of components. What is that principle? The number of components C equals to number of constituents C dot minus number of independent chemical equations Z and the number of additional restricting conditions R. Now this equation actually valid for reactive systems. We will discuss it later on. And for non-reactive systems, for the reactive systems, so C equals to C dot minus Z minus R, where C dot is the number of components, C dot is the number of constituents, Z is the number of number of equations, and R is the additional restricting conditions. Now for non-reactive systems, the number of components is equal to the number of constituents. Here C equals to C dot, Z and R are not considered in this case. So for reactive systems, number of components C equals to number of constituents minus number of independent chemical equations minus number of additional restricting conditions, that is C equals to C dot minus Z minus R. And for non-reactive systems, number of components C equals to number of constituents. Let we understand this with some examples. Now, dissociation of ammonium chloride. Ammonium chloride solid dissociates to give NH3 gas and HCl gas. This system has two phases. This ammonium chloride is a solid, it is one phase, and NH3 and HCl is a mixture of gases, so this constitutes another phase. This is a single phase and this is another phase. So there are two phase system. solid ammonium chloride, and gaseous phase contains NH3 and HCl. Now, two cases may arise. If the dissociation is carried out in vacuum, then the number of components of the system is 1. Why? This is due to the fact that in gaseous phase, both HCl and NH3 are always present in equal amounts, and thus the composition may be represented by NH4Cl. If we want to express the composition of NH4Cl, then it is sufficient to say that XNH3 plus XHCl. So the solid phase NH4Cl can be expressed as NH3 and HCl, and the gaseous phase as well can be expressed as NH3 and HCl. So two constituents are here sufficient to express both the phases. Now, if we use the equation to calculate the number of phases here, then C equals to C dot minus Z minus R. Now, there is an equation. Which equation? The dissociation equation of ammonium chloride. So, this is the dissociation equation of ammonium chloride. So, there is one equation. So, Z equals to 1. Again, NH3 and HCl constitute a single phase and produced in the ratio 1:1. So, there is an additional restricting condition that the amount of NH3 and HCl are equal, that is XHCl equals to XNH3. So, this is an additional restricting condition. So, here R equals to 1, therefore C equals to C dot minus Z minus R. C dot equals to 3, that is the 3 constituents are there, NH4Cl, NH3 and HCl. 1 is for the equation NH4Cl reduced to NH3 plus HCl gas, and 1 is for the additional restricting condition, that is equal amounts of NH3 and HCl in the gaseous phase. So this is equals to 1. So we get it is a one component system. Now, if ammonium chloride dissociates in presence of arbitrary amounts of NH3 gas or HCl gas, or in presence of both HCl, arbitrary amount of HCl and NH3 gas. The additional restriction here, that the presence of NH3 and HCl in the system in 1:1 mole ratio is no longer valid. That is, in the gaseous phase, we cannot say that XNH3 equals to XHCl. Rather, we can say that this XNH3 plus YHCl. We cannot say that in presence of arbitrary amount of HCl or NH3, we cannot say that the gaseous phase contains is represented as XNH3 plus XHCl. Rather, we can express it as XNH3 plus YHCl. So, the additional restriction, that is the equal amount of NH3 and HCl, is no more valid. Hence, R equals to 0. Hence, the number of components C equals to C dot minus Z. R equals to 0, since R equals to 0, so this is 3 minus 1, this is 2. That is a two-component system. Another example. This example is the dissociation equilibrium of calcium carbonate solid at higher temperature. And the dissociation can be represented as calcium carbonate, calcium oxide plus carbon dioxide. Here the number of phases are 3. This is solid, this is another solid, and this is gas. So this is one phase, this is another phase, this is another phase. So the number of phases is 3. The number of components in the above system is 2, although there are 3 substances at equilibrium. Here the number of components will be 2, although there are 3 constituents or substances at equilibrium. This is because in the above system, 2 species out of the 3 are sufficient to express the composition of all the 3 phases. I do repeat, this is because in the above system, 2 species out of the 3 are sufficient to express the composition of all the 3 phases. It is immaterial which of the two are selected for this purpose. Now, if calcium and carbon dioxide are chosen, then calcium carbonate solid, this can be represented as calcium oxide plus carbon dioxide. Calcium oxide solid can be represented as calcium oxide plus 0 carbon dioxide. Carbon dioxide gas can be represented as 0 calcium oxide plus carbon dioxide. Now, if calcium carbonate and calcium oxide are chosen, then we can say that calcium carbonate solid equals to calcium carbonate plus 0 calcium oxide. Calcium oxide solid equals to 0 calcium carbonate plus calcium oxide. Carbon dioxide gas equals to calcium carbonate minus calcium oxide. So, every phase is represented by 2 of the 3 constituents. So, this is a 2-component system. Hence, C, if we use the equation C equals to C minus Z, there is no restriction at all. Therefore, C minus Z, because there is one equation, the dissociation of calcium carbonate. So, this 3 minus 1 equals to 2. Here we cannot use the additional restriction. Why? No additional restriction is there. Although dissociation of calcium carbonate in a closed vessel produces calcium oxide and carbon dioxide in the mole ratio 1:1. So there might be some additional restriction, but we are not considering the additional restriction here. Why? Because calcium carbonate and carbon dioxide are in different phases. They are in different phases. And each phase, and in each phase, mole fraction of the constituent is unity. So in calcium oxide, it is in solid phase. So in this solid phase, its mole fraction is a unity. There is no other thing. And carbon dioxide, it is in the gaseous phase. In its gaseous phase, there is no other substances. Its mole fraction is unity. Therefore, the additional restriction here has not been taken into consideration. Therefore, C equals to 3 minus 1 equals to 2. Now, some other examples. Now, solution of sodium chloride. If we take the solution of sodium chloride, if sodium chloride is considered as a compound in the solution, then the number of components will be 2, that is sodium chloride and water. But considering the dissociation of sodium chloride and H2O, we have Na plus ion, Cl minus 1, H2O, H plus ion, and OH minus ion as individual chemical species in the solution. So, if we consider the dissociation of sodium chloride, sodium chloride is a strong electrolyte, so it will undergo dissociation. So, if we consider the dissociation of sodium chloride, so in the solution we will have Na plus 1, Cl minus 1, and further, if dissociation of water is also considered, then we will get in the solution pure water molecule, H plus 1 and OH minus 1. So, in total, there will be 5 individual chemical species in the solution. Now, there exists a reaction H2O, H plus plus OH minus. This exists in the solution. The question may arise why dissociation of NaCl is not taken into consideration, because sodium chloride is a strong electrolyte. It will instantly undergo dissociation to form sodium and chloride ion, and sodium and chloride ion will not recombine to form sodium chloride again. So there is an equilibrium reaction, so it is not taken into consideration. Relations and restrictions to be found out to calculate the number of components in the system. Now it is our job to find out the number of components in the system. We have to find out the relations and restrictions. There exist additional restrictions as follows. The sodium chloride, concentration of sodium chloride, sodium ion, and the concentration of chloride ion will be same, because 1 mole of sodium chloride will give 1 mole of sodium ion and 1 mole of chloride ion. And second, another restriction is there, that is electroneutrality or charge balance. This is the left hand side is the summation of positive charges, and right hand side is the summation of the negative charges. So since the solution is electroneutral as a whole, therefore summation total positive charge must be equal to total negative charge. So this is another condition. So we see that here C equals to C dot minus Z minus 1. Here C dot equals to 5, total number of individual chemical species is 5. 1 is the equation, this is the equation, H2O is in equilibrium H plus OH minus 1, this is another equation, and this is the equation, and there are two restrictions, that is the XNA equals to XCl, and the other one is the electroneutrality, that is XNA plus XH plus equals to XCl minus plus XOH minus. So here the number of components equals to 2. Then we will discuss the degrees of freedom. Now what is the degrees of freedom? The degrees of freedom, the number of degrees of freedom or variance of the system is the minimum number of independent variables such as temperature, pressure and concentration that must be specified in order to define a given system at equilibrium completely. The number of degrees of freedom or variance of the system is the minimum number of independent variables such as temperature, pressure and concentration that must be specified in order to define a given system at equilibrium completely. That is, we have to define the system completely at equilibrium. So the independent number of variables, there is temperature, pressure and concentration, so on and so forth, must be specified to define the system at equilibrium completely. This can also be defined in another way. The number of degrees of freedom of a system is the number of factors, temperature, pressure, concentration, etc., which can be varied independently without altering the number of phases. So, the factors, the temperature, pressure or concentration, which can be varied independently without altering the number of phases. This may be explained with various illustrations. We will try to explain this with various illustrations. Let us consider, first of all, a gas is